Hello, welcome back to Algebra 1. We are in Module 4b. And all that means for us is that we're continuing our Unit 4, but this is the second section of it. So it's all in the same module online if you're following along in the online book. And today's lesson is going to be Algebra 1, 4b, Lesson 1, and lesson 2. That means page 1 and page 2 for us. And the reason I've combined them is because on page 1 of the lesson this time, the vocabulary is the same as it was in the first one in lesson, just plain old unit 4 or module 4. So I didn't feel a need to go back over those same vocabulary. If you need to go back over the vocabulary, please refer back to lesson 4.1, which does cover that vocabulary. However, we do have some important questions that we're going to go over because we need to make sure that we know what we're going to be talking about in this chapter. How do I build an exponential function that models a relationship between two quantities? In other words, I got two pieces of information and I want to know how they relate together. One of them increases exponentially. How do I write that equation? How do I write that math sentence? Number 2, how do I build functions from existing functions? So I already have a math sentence. They need to change it in some way and make a new one. How do I use exponential models and functions to interpret and analyze real-world situations? So I've created this model, this mathematical model or math sentence based on the information that I have. How do I use that to find the information that I'm looking for? And then why are geometric sequences functions? We'll get into that too. And how can we use real-world situations to construct and compare exponential models and solve problems? So those were the questions we're going to get to in Unit 4b. So let's jump right into it. Exponential growth models. So section 4a, the first part, we learned about exponential growth and exponential decay and what the functions were and the graphs were. And when we put that into models, that means we're going to be looking at real world situations and creating our equations and our graphs out of these real world situations. Some people call them word problems. So this is the word problem section. All right, so Jane buys a rare trading card and it's going to cost Jane $5 to get that card. Now, this card could be a baseball card or a Pokemon card. It doesn't tell us, just a rare card, and it costs $5. This card increases in value by 40% every year. How much will Jane's trading card be worth in 3 years? All right, so I've gone in with my pen and I've kind of highlighted some important information that we need to pay attention to. And I think the best place to start is going to be by making a table. And so I have here a table, our input value, the years owned, and our output value, the value of the card. So before she owned it, or the first year that she owned it, how much was it worth? It was worth exactly what she paid for it, $5. Now, this increases by 40% every year. So the first year, it's going to increase by 40%. Well, how much is 40%? We have to take that $5 and multiply it by 40%. And remember, when you multiply by a percentage, you need to change it to a decimal. So you're going to move the decimal 2 places. So it's 0.4. And then you're going to input that into your calculator. So 5 times 0.4 is $2. Okay, so is the trading card worth $2? No, it increased in value by $2 because it increased in value by 40%. So we need to take this increase and add it to the original amount of $5. So altogether, that the value of the second card is $7. And if I wanted to write this as a single problem instead of 2 separate problems, it would be 5 plus 0.4 times 5 equals, and there's that 5 plus 2 again, equals $7. So you can see how you can do it all in one mathematical sentence here by taking the value and then adding the 0.4 times 5. And that's how we're going to get that. So let's look at 2 years. So the value we're adding to this time is 7 and not the 5, okay? So I'm going to come up here with an equation. 7 plus 0.4 times 7 equals what? Well, let's put this in my calculator. 7 plus 0.4 times 7, enter, 9.8. So $9.80. Okay, so then for 3 years, I'm going to do the same thing. 9.8 plus 0.4 times 9.8. And what is that going to equal? Let's put it into the calculator. 9.8 plus 0.4 times 9.8. That equals $13.72. So after 3 years, Jane's card will be worth $13.72. After 3 years, Jane's card is worth $13.72. All right, so we answered the question, but there's some things we need to notice in here. Notice that every time we calculated the new value, we used the previous year's value, and then we found 40% of that and added it back to the original. So in other words, to get this formula, you do the old value plus 40% of the old value equals the new value. So you see what we did is we just multiplied and added. We multiplied by the percentage and added to the last amount. Let me clear this. Sorry about that. All right. So when you notice that the values don't have a constant difference. So between 5 and 7, we had a difference of $2. Between $9.80, 9.8 minus 7, it was $2.80. And then between 13.72 and 9.80, we had a difference of $3.92. Sorry, didn't read that correctly. 92 cents. So you see that the difference between them is never the same. So it's not growing in the tradition, the geometric sequence like we looked at before. It's growing, or the sequence type that we studied before, is growing in a ratio. And so if we want to determine that rate, what we do is we simply divide each new value by that year's previous value. So 7 divided by 5 instead of subtracting by 5, and then 980 divided by 7, and then 7 divided by 5, right? So all of these, every single time we divide instead of subtract, we get 1.4. Now, why 1.4? Well, the 0.4 should be obvious because the 0.4 is our 40%. Well, what is that 1? Well, what is 1 as a percentage? If we had 1 here and we moved our decimal 2 places, that's 100%. What is 100% of 5? It's 5. What's 100% of 7? It's 7. So if we took 5 and multiplied it by 1.4, or 140%, I bet we'll get 7. Let's try it in the calculators and see. 5 times 1.4 equals, it is 7. I bet we could do that for each one of these since our ratio is 1.4. So 7 times 1.4 is 9.8. And 9.8 times 1.4 is 13.72. So if I'm having to, when I multiply by this ratio of 1.4, instead of doing the multiplication of the 40% and then adding in the last value that I had, I can just multiply by 1.4 instead of doing all that other math. And that reduces it down to just one problem. And we actually have a formula here that will remind us of this rule here of how we combine that. So here's our formula. F of t is, we're looking right here in the center, F of t is A times 1 plus r, and that addition problem, 1 plus r, is raised to the power of t. Now, this is a formula. That means we're going to be inserting a lot of different things into here. And so we need to know what each of these letters represent, okay? The first thing that I want to notice here is the f of t. The f of t is the name of our function. It tells us that this function has an input value of t. This is our input value. So we know that t will stay in the equation. No matter what, we're going to have t as the input value or the independent value, right? And f of t is going to be our dependent value. So let's jump over here to t. T is the time interval. This is the independent variable, or what we used to be calling x, right? And this is the dependent variable, because whatever this f of t is, we don't know until we know what t is. F of t depends on what t happens to be. All right, so A right here, this one, A, is the initial value. And if you're working with money, it might be the principal, or in the case of the last thing that we looked at, it was 5. The initial value of the trading card was $5. So that initial or starting amount goes here where the A is. R right here is the rate of change, or in this case, since we're working with exponential growth, it's the growth rate. So it's the rate of the growth, the rate of change as it's increasing. Okay. So you should have this written in your notes. If you don't have it written in your notes, pause the video and write it down. I want to see it on your paper. All right, so exponential growth models. Let's check out the equation and graph of a growth of Jane's playing card. So this is her playing card. Remember, we said she started out, her playing card value was $5. The growth rate was 1.4. We determined that by dividing each of the numbers, right? Or you could say that she increased 40%, plus the 100% when we added it together was 140%, or 1.4 as a decimal, right? And it's raised to the power of t. And remember, that's time. And that's what our independent value is. And that's why it's still t here. So we're going to not, that varies based on what we inputted, whether it's 1 year or 5 years or whatever it may be. So let's look at what this looks like on a graph. Notice this graph starts here at the 0. There's no possible way for it to be going into the negative, because the negative would be if she had the card for -2 years or -7 years. That's just not possible. So she can only have the card for a positive number of years. So this is starting here at the y-intercept and moving in this upward exponentially function, this exponential growth direction. So we've got some questions we want to answer here. So the first question I want us to look at is, what is the y-intercept of the graph, and what does it represent? So here's the y-intercept. You see it's on the y line. So how do we know what that is? How are we going to figure that out? Well, what we need to do is get an ordered pair. Remember, when we have a y-intercept, our x is always 0, and our y is whatever this number is. So this graph is kind of hard to see the way I have it laid out, but this is 0, this is 5, this is 10, this is 15. So right here, where this dot is, where the line of the graph is crossing the y-axis, is 5. So that's our y value for the y-intercept. What is the growth factor of 1.4 written as a percent? Well, we've already talked about that. That's 140%. All right, now we're going to use the graph to estimate the value of the card in 2.5 years. So what we have to do is, since our input value is time, we know it's the X value or this horizontal value. So we're going to find out what 2.5 years is. And I don't know if you can see that, but that's 1, 2, 3, and 4. So 2.5 is right about here. And we're just going to follow this line all the way up till right about here. Okay. And that's where it crosses the line. So where is this on the Y? Well, if this is 15 and this is 10, 1, 2, 3, 4, 5, there's 5 things in between that. So 10, this is 11, and this is 12. So it's 11.5. We can estimate, because we don't know exactly, but that does look like where it is, that it'll be worth $11.50. Okay, question 4. What is the domain in the context of the problem? Now remember, our domains for exponential functions that we talked about in our first section was always the set of all real numbers, right? Because domain is our input values or our X values. You could input anything you wanted and come out with an answer. However, when you're working with models or real life problems, sometimes the domain will be limited, just like it is here with Jane and her card. It's not possible for her to own this card for a negative amount of years. We already said that, right? So it means that if this graph were to continue over in this direction, exponential would go continuously down, right? This is not possible because she would have to own the card for a negative amount of years in order for that graph to continue on in that direction. So the domain in this case cannot include those negative numbers. So X has to be greater or equal to 0. So 0 or greater, okay? Or in this case, T, not X, excuse me. T is greater than or equal to 0. So I hope you were able to understand or get correct all of those questions when you went through them on your own. All right, so Tom purchased 200 worth of stock and his broker estimates it's going to grow by 10% each year. So let's go ahead and highlight some of these important pieces of information. $200 worth of stock is important. $10 every year is important. Write the function and estimate how much it'll be worth after 3 years. That's the question. That's what we want to find out, 3 years. So first we need to write a function before, or a mathematical sentence, an equation, before we can figure out what it's going to be worth in 3 years. Now, if you don't have the equation written down in your notes, this is a time for you to pause the video, go back and find it, and write it in your notes. If you do, you should already know what the equation is. F of t is a times rate to the power of t. Okay, now remember what A is. A is the initial worth, initial amount. That's $200. So F of t is 200 times, what is the rate? It's going to grow by 10% each year. So is it only going to be 10%, or is it going to grow by 10% plus this original? Well, if it's increasing, it's going to grow by 10% plus the original. So 1.1, right? Each year. So T, we know, is going to be in years. Okay. So how much will Tom's stock be worth after 3 years? All you have to do is plug into your calculator 200 times 1.1 to the power of t. So we have to use our caret here, the caret button on your calculator. On some calculators, it's right above the division symbol. On others, you might just have to look around, but it looks like the top part of a triangle, okay? And that's going to allow you to raise up to the exponents. Now, so 200 times 1.1, or open parentheses 1.1, close parentheses, caret. Now, instead of putting t in or x, we're going to input here the number 3, because that's what we want to know. So 200, open parentheses 1.1, close parentheses, caret 3. And so let's go ahead and do that. 200 parentheses 1.1, close parentheses, caret 3, enter. So my calculator tells me he will get $1,597.20 in 3 years. What if we said, estimate how much his stock will be worth after 1 decade? Well, you have to know that a decade is 10 years. Or what if we said after 18 months? Okay, 18 months. Well, how many years is 18 months? You're going to have to transfer this information from months into years, because we're inputting years here, because it says 10% each year. So 18 months is a year and a half, so 1.5 years. So you would input for t 1.5. Okay, so you have to always pay attention to your units of measure, your time, and any kind of unit of measure, especially on real world problems or word problems. All right, so here's the same question. We have $200 worth of stock that Tom purchases, and his stockbroker is telling him it's going to increase by 10% each year. So, but what they're actually asking us to find is a little bit different. They're asking us, how many years will it take for Tom's stock to be worth more than $500, right? So I'm going to go ahead and write down what our problem was that we came up with last time. I think I'll write it right here. So we had f of t is 200 times 1.1 to the power of t, right? Now, I'm going to show you the best way to do this is to use a calculator. I don't want you doing any kind of extra work. So I have a calculator app on the computer here. And so this calculator here may be similar to some of the calculators that you have there. There's the caret button. It looks like the top part of a triangle, you see. So how do we enter this? I don't know if you can see what I wrote, so I'm going to write it over here. F of t is 200 times 1.1 to the power of t. And we wanted to know, how long will it take to get to $500? Well, is that $500 going to be the output or the input? In other words, the dependent or the independent variable? Well, that would be this output or dependent variable. So it would go in place of where this f of t is right here. So we can't just plug it into a calculator and find out the answer. One way you could do this is you could create a table of input and output values. So time and the function of time, and you could plug in, okay, after 0 years, it's $200. After 1 year, it's this, and you could keep going until you get to be over $500. However, you know, sometimes these equations may get to be so long and so big that you'd have to do that 100 times before you could find it out. So we're going to look at a different way here. this is a graphing calculator. So some of these, we're used to these numbers down here because that's the math we normally do. But the graphing calculator has this y equals button here. So when we click y equals, it allows us to input an equation and look at a graph. So when I input it here into the calculator, I have to use y and x instead of f of t and t. So it already has y in there. It's going to be y1 because you could enter more than one equation. So that's what the 1, 2, 3, 4, 5, 6, and 7 are for. But y equals, and then we're going to put 200, and we're going to have to put in the parentheses. Oops. Let's put in the 0.1, close the parentheses, and now we have to put the caret button, and you see how it automatically puts it up as the exponent for us. And then again, there's not a t that we're going to use, so we're going to use the x value here. And so we have 200 times 1.1 to the power of x. And if you want to see what that graph looks like, you can look at graph. But this is so large, it's not going to fit in your default standard screen. You would have to adjust your window in order to see the graph. So it looks like nothing to us, but there is something there. We just can't see it on this screen. But that's okay, because what we're looking for, I don't want to see the graph. I want to see a table. Just like I said, we could create our own table, but we don't know how far. We'd have to do all that math and find the answers. So instead, we're going to let the calculator create the table for us, and we're just going to look at it to find the answers. So if you can see these blue letters up here on the top of the calculator, I'm actually going to see if brightening this up helps at all. I don't know if you can see it, but this one right here says table. It's right above graph. We pushed graph to get to this point. But when you see a blue thing, if you want to get to that, you push the second button first. So we're going to push second, table, and it brings us to the table. Now we're looking for when the y value goes over 500. So it started at 0, and let's go down. There's 354, 389, 428, 471, $518. So in the 10th year, it will go past the $500 mark, because in year 0, his initial investment, he put in $200. By the end of the first year, he had 220. By the end of the second year, he had 242. By the end of the third year, he had 266.2, et cetera, et cetera. So it is by the end of the 10th year that he has $518.75. So at some point in the 10th year is when he will hit that 500 mark. So it is the 10th year in which he breaks the $500 mark. Okay, so how would we write that as an answer? How many years will it take Tom's stock to be worth more than $500? It will take Tom's stock 10 years to be worth more than $500. Okay? With word questions, you give word answers. And hopefully your handwriting looks better than mine. All right, an exponential growth model. A scientist is researching the growth of certain bacteria. He starts with 200 cells. Okay, that looks like important information. It's something he starts with. That must be my A, 200. Remember, our formula was F of T equals A times R to the power of T. Okay, you should have that in your notes. All right, so he starts with 200 cells of a certain bacteria and notices that the bacteria triples each hour. T is going to be hours, and it triples. So our rate is it triples. Oops. triples. There we go. Write an exponential growth model to describe the growth of the bacteria. And how many bacteria will there be after 1 day? So that's the question that we're looking for after 1 day. We have to start with writing an equation. I know that f of t is going to equal A, which I know is 200 cells, times R. What is my rate? Well, if it triples, then I multiply that by 3 times to the power of T, which is in hours, right? So I have my equation here. And what is it that I have to do? It says after 1 day. So do I put a 1 in for the T? No, that's not what we do. When we see 1 day, remember our T is in hours. So 1 day is 24 hours. So f of t equals 200 times 3 to the power of 24 hours in 1 day. So I'm just going to enter this into my calculator by doing 200 open parentheses 3 close parentheses caret 24 and hitting enter. 200 open parentheses 3 close parentheses caret 24 and I hit enter, and what I get as an answer is 5.64859073 plus, oops, not lowercase e, capital E, sorry, capital E plus 13. Well, what does this mean, E plus 13? That means that this is in scientific format, which means I'm going to have to move my decimal place 13 places. So I need, because of the plus, I know my number is going to get bigger. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8. So 5, 6, 4, 8, 5, 9, 0, 7, 3 was 8, 9, 10, 11, 12, 13. That is how many bacteria there are after 1 day. Wow, that increased so fast. You'd think it's exponential or something. All right, exponential growth models practice. I need you to pause the video, work this out yourself, and then come back and we'll go over it. In case you can't read this first one here, if the video is in the way, I will read it to you. It says, Jill deposits $300 into an account that earns 15% simple interest each year. Write an exponential growth model to describe the balance of Jill's account. Okay, pause the video and start working on it. Welcome back. Jill deposits $300 into an account that earns 15%. So I know that A is going to be 300. R is going to be, well, I know that 15% is going to be added to the 300. So it's 1.15. And then T, simple interest, it says each year. So T is going to be in years. So write the model to describe the balance on her account. Okay, so F of T is 300 times 1.15 to the power of T. And that is the answer to question 1. How much money will Jill have after 5 years? Okay, well, I'm going to put it into my calculator, 300 times 1.15, and then I'm going to use my caret, and I'm going to insert 5. It's years, so I can just stick it in to the T location, right? So caret 5. 300, open parentheses, 1.15, close parentheses, caret 5, enter. And I get 603.4, it says 407. Since this is money, we're going to round to the nearest cent and say 41. So this is $603.41 after 5 years. Approximately when will Jill have $1,000 in her account? Okay, $1,000 in her account. I'm going to have to get out of this to look at the let's write this over here, 603.41. And then it was f of t is 300 times 1.15 to the power of t, because I'm going to have to get out of this and use my calculator for you to be able to see it. All right. Here's the calculator. So to get back to my y equals, I have to go to y equals again, and then I'm going to clear this out. And I'm going to input my equation, which was 300, open parentheses, 1.15, close parentheses, caret x. And then I don't even want to bother looking at the graph, so I'm just going to go ahead and go straight to the table here. And we're looking for, oops, let's see. Oh, I see what I did wrong here. I had pushed something different instead of, there we go. I don't know if you saw that, but I had a curly bracket there instead of a parenthesis. So that's what my problem was. I'm going to go straight to the table. And let me look back here. What was it we were looking for? We want to know when will Jill have $1,000 in her account? Okay, so we want to look at the y values and see when it gets to be $1,000. And it's right here. Year 9 is $1,055.04. So it's in the 9th year that she's going to break that $1,000. So let's go back here and write our answer. After 9 years, or in your, I apologize, let's erase that. It is in the 9th year. In the 9th year, Jill will have $1,000 in her account. Lane's parents have offered to double his allowance each month. Double, that's what? That's times 2, right? Double his allowance each month. That's important information. Let me go ahead and change my pen color here. Double his allowance each month. He starts earning $1 in the first month. Write an exponential growth model to describe how much he earns each month. So we have our f of t, and he starts out earning $1 times a rate of 2, right? Because that's how it doubles, is times 2 to the power of t. And we know that t is months, right? So this is the exponential growth model that describes how much Lane earns each month. So that will help us on this next question. In which month will Lane earn $128? Okay. We have to go back now to the calculator. I'm going to erase some of this so we can look at the calculator. All right, so we're going to go back to y equals, and then I'm going to clear this because that was an old problem. We no longer need that. And it's 1 parentheses 2 parentheses caret x. And then I'm going to go to the table, and the question was, when will he have earned $128 for the month? So we want to see where the y value is 128. And you can see right here that it is at the x equals 7, y equals 128. Okay. So after 7 months, he will have earned $128. So hopefully you got all of those correct. remember this one was 9 years. 9 years. And then this was 7 months. The 7th month. All right. All right, so we are almost done, but there's one more type of exponential growth I want to show you. This one is specific to banks and interest rates. So there's two different ideas with interest. There's an interest that if you put money into a savings account, the bank will pay you to hold on to your money. And then another kind of interest is when you use a credit card. If you use a credit card and carry a balance, you have to pay the bank money. You have to pay them interest in order to be able to do that because you're holding on to their money, just like they paid you when you had a savings account and they were holding your money. If you use a credit card, you're using the bank's money. You're holding on to it by buying stuff. And so you have to pay interest on that. And so those are the two types of way. Now, this has its own formula that's just a little bit different than the traditional exponential growth formula. This one, we add an n into the equation. So here our a has turned into a p, but it's essentially the same thing. So it's a times, normally we know what the rate is, goes right here. But in this case, what we're doing is 1 plus that 1, remember, is going to get us that 100%. It's going to add whatever interest was earned to the last amount. That's what this 1 plus means right here. Okay, 1 plus. And then our rate now is going to be a part of a fraction. Because if you notice, this says compound interest. And that means that there's going to be different times where they might calculate the interest. Sometimes it's compounded daily. Sometimes it's compounded monthly. Sometimes it's compounded annually or quarterly. And so we need to know what that means. That means compounded means when it's calculated. Okay, so the rate is just as important as how often they calculate how much money to give you. So they take the rate because it's an annual rate, meaning a per year rate, an annual interest rate, and they divide it by how many times they're going to calculate it for you or compound it. So that's what n is. N is the number of times compounded or calculated every year. In the problems, it'll say compounded monthly or compounded annually, but it just means calculated. And then if you notice, there's two n's, 1 and 2. Okay, there's an n and there's an n. So not only is n going to adjust the rate a little bit for us, it also adjusts the exponent here because our exponent is being multiplied by n. And then t, excuse me, is the time interval because the rate is always an annual percentage, an annual interest rate. So our time interval is always in years. And so because our time value is always in years, our compound, we need to know how to find some numbers for that. If it says it's compounded monthly, then n will be 12. If it says it's compounded daily, n is 365. So you get what's happening here. If it's monthly, that means how many times does that happen in 1 year? 12. If it's daily, how many times does that happen in 1 year? 365. If it's yearly, oh, well, that only happens once a year. So it's just 1. And quarterly happens 4 times a year. So these are the numbers, the only options really that I could think of that you would be inputting for n at any given time. And remember, you're going to input it into 2 different places. And P is the initial deposit or the initial amount of money that's being charged the interest. It's essentially what our A was before. And in this case, a capital A is your final amount. So again, pause the video, write this down, including what everything is in your notes. We will be using this on the next screen, and you need to know what the formula is. All right, compound interest. Let's say you deposit $1,500 into an account that earns 5% interest annually, compounded monthly, an annual interest rate of 5%. It does not say annual interest rate, but all interest on bank accounts are annual interest rates. And it's compounded monthly. This means that, let's see, is there something else? Yeah, there we go. It has it for us. P is 1,500. So P stands for principal, or the initial investment. The starting value, 1,500. And our rate is 5%. And as a decimal, that's 0.05. Okay, so 5%, 0.05. 1,500 is our P. And it says it's compounded monthly. That means our N is going to be 12. So how does this translate into an equation? Let's put all of these numbers into our equation. And we have here A equals 1,500 times 1 plus 0.05 divided by 12. All of that in parentheses to the power of 12 times T. So it's a little more complicated only because we now have these two N values, these 12s right here. All right. Now, let's look at this. Well, let's go back to this equation. It doesn't ask us this, but I want to know how much would this person, you, earn after 2 years? Okay. After 2 years, how much would you earn? So we need to figure out how to plug this into the calculator. So it'd be 1,500 times 1 plus 0.5 divided by 12, close parentheses, caret. And then you have to put in parentheses 12 times 2. So our 2 right here went into the place for the T because we had 2 years, and T is always years. So this works. We can just plug it in. But you have to pay attention to when you're using this caret. It will only apply the first number if it's not in parentheses. Okay, so you have to have those parentheses in there. So let's go ahead and plug this into our calculator. 1,500, open parentheses, 1 plus 0.05. I put 0.5 there. It's 0.05. It's supposed to be like that. There we go. Divided by 12, close parentheses, caret, open parentheses, 12 times 2, close parentheses. Now, if you don't want to enter this second set of parentheses here, you could write it this way: 1 plus 0.05 divided by 12, close parentheses, caret, and do this math prior to. So we know that 12 times 2 is 24. So you could enter it in like that, and you would get the correct answer either way, which in this case, after 2 years, you would have in your account $1,657.41. All right. When she was born, Molly's parents deposited $200 into a savings account that earns 12% interest, compounded daily. How much money will Molly have on her 16th birthday? I bet you can figure this out. Pause the video and go ahead and give it a shot. All right, welcome back. Molly's parents deposited $200. That means P is going to be 200. It earns a rate of 12%. R equals 0.12 because I need that as a decimal, right? I know that N is compounded daily, so N is going to be 365, and T is always going to be in years. So I'm going to have A equals 200 times 1 plus R is 0.12 divided by 365 to the power of 365 times T. Okay. Now the question is, how much money will Molly have on her 16th birthday. Well, her 16th birthday, 16 years have passed. So we can plug that 16 into where the t is. So let's see how this would go into the calculator. 200, open parentheses, 1 plus 0.12 divided by 365, close parentheses, caret, open parentheses, 365 times 16. It's a times right there. Now, another way you could do this is you could take your calculator and just do 365 times 16 and figure out what that number is. And it's 5,840. So you could instead do 5,840 instead of the parentheses here. But I'm going to do it the original way. 200, open parentheses, 1 plus 0.12 divided by 365, close parentheses, caret, open parentheses, 365 times 16, close parentheses, hit enter. Okay, so if Molly's parents put in $200, that's it, just $200, after 16 years on her 16th birthday, she will have $1,363.76 because we round to the nearest penny because this is money. So that's quite a bit of money she earned there from her parents' initial investment of $200. So go parents, yay Molly. 2 questions for you and then we're done. Go ahead and pause the video, figure these out, work these on your own, and then come back and we'll do them together. Jason deposits $700 into his account. So P is 700. It earns 7% interest. So R is 9% or 0.09. Because remember, it moves 2 places, the decimal point, to get to the decimal for the percent. It's compounded quarterly. So N equals 4. How much will Jason have after 6 years? All right, so let's write a problem. A equals 700 parentheses 1 plus the rate 0.09 divided by N, which was 4, close parentheses, and then N times T. All right, so the question is, how much will he have after 6 years? So what am I going to plug into my calculator? I'm going to do 700, open parentheses, 1 plus 0.09 divided by 4, close parentheses, caret, open parentheses, 4 times 6, close parentheses, hit enter. Oops. If you close your parentheses, but you don't open them, you get a lovely error message letting you know that you've messed up. So that is good. All right. The answer is $1,194.0366. So we're going to say 04 because we need to round up to the nearest penny. So $1,194.04 is how much Jason will have after 6 years. Harriet deposits $1,200 in an account that earns 6% interest. P is going to be 0.06. And it's compounded monthly. So N equals 12. How much will Harriet have after 10 years? Okay. A equals 1,200, 1 plus 0.06 divided by 12 to the 12 times T. All right, now I'm going to, because 10 is years, go ahead and just plug that into my calculator. I'm not going to write it out for you this time. You should know how to plug it in to the calculator on your own at this point. And I got $12,740.13. So there you go. That's how you compound interest. And this is definitely math you will use a lot of times. Students ask me, oh, when will we ever learn this, Miss, actually use this in real life? And you know what? Sometimes the answer is Probably never. But in this case, you might actually use this in real life. This is good information to know. If you want to know how much money you need to deposit today in a money market account or an interest-bearing account in order to be a millionaire by age 30, you can use this formula to figure it out. So this is a very functional exponential growth equation or function model that you can use. All right, we'll see you in the next lesson.